Steinhauer here, welcome back. We have seen how Edwin Hubble used Cepheid variables in the Andromeda Galaxy to measure the distance to the Andromeda Galaxy. He didn't stop there, and in fact, he's most known for this next discovery, which is that he went out and he measured the distances to lots of galaxies, and he correlated that distance with something else, and that's become known as Hubble's law, and it's one of the most important laws in all of cosmology and all of the universe, really. And that's what we're going to talk about now. So first, let's talk about how galaxies appear in their spectra. It turns out that pretty much every galaxy in the sky has its spectrum redshifted. What does that mean? It means that when we see particular absorption lines in a galaxy, those absorption lines have been shifted well to longer wavelengths than they are at galaxies that are not moving with respect to us, or where we know stars that emit those absorption lines should be if they weren't moving with respect to us. So that's really interesting. Almost every galaxy in the universe, its spectra has been redshifted. And this redshift can be significant. This is an example of a 5% redshift. That's very unusual. That means, as you may remember from the Doppler effect, the way to get a spectrum to be completely redshifted is to have that object moving away from us. Objects that are moving away from us have positive radial velocity, and their spectra will be shifted to the red, just in this way. But a 5% redshift is big. That means this object is moving away from us at a significant fraction of the speed of light. So this is unusual for lots of reasons. First of all, sure, stars are redshifted too, but they're blue shifted as well. So you look at a random population of stars, some of them are moving towards us, some of them are moving away from us. For galaxies, it seemed to be that virtually every one of them is moving away from us. Does it matter what kind of galaxy it is? It turns out it does not. If we look at elliptical galaxies, and we look at spiral galaxies, and we look in that part of the sky, we look in this part of the sky, we always get a diagram that relates their velocity, how fast they're moving away from us, to the distance. And this is a very nice diagram that goes up something like that. We'll see it better in an upcoming slide. But I want to first think about these radial velocities because they're really big. Here are as an example of a few of them. We're going to do a lab on the Hubble law coming up. But look at these radial velocity shifts. Here's a galaxy in the Virgo cluster. You can see we're going to use the method of standard rods to get the distances of these galaxies. But the bigger they are, the closer those galaxies are to us. This is in the Virgo cluster, the Ursa Major cluster, and the Corona Borealis, and the Bootes and the Hydra cluster. And you can see you're getting fainter, smaller and smaller as you go down, and therefore further and further away. Well, these are two lines. There's two prominent lines in stars, the H and K lines. And we know where those appear in normal stars, right? And we can say, hey, the Virgo cluster is moving away from us at 1,200 kilometers per second because these two have been shifted to the right by a certain amount, right? Here are those lines in the Ursa Major cluster. Look at how far they've been shifted. This cluster is moving away from us at 15,000 kilometers per second. Here they are in the Corona Borealis cluster, 22,000 kilometers per second, all the way over here in Bootes and all the way out here in Hydra, 61,000 kilometers per second. This is a staggering number, 61,000 kilometers per second. In fact, let's think about that number briefly. What fraction of the speed of light is that galaxy moving away from us? Its velocity was about 60,000 kilometers per second. You might remember that the speed of light in that same unit is 300,000 kilometers per second, or 3 times 10 to the 5 kilometers per second. It's 3 times 10 to the 8 meters per second, but in kilometers per second, you take away 3 of those zeros, it's only 3 times 10 to the 5, or 300,000. So V over C is 60,000 kilometers per second divided by 300,000 kilometers per second. These units cancel out. This is going to be a unitless number, but what is the number? it is 0.2. The galaxy on the previous page and every single star in it is moving away from us at 20% the speed of light. How do you get a galaxy, an entire galaxy, moving away from us at 20% the speed of light? That is the mystery that we have to unravel in this particular section. But so this is a more modern view of the Hubble diagram. Again, the idea is, and the thing that Hubble discovered was that the further away a galaxy is, the faster it's moving away from us. This, again, is really weird. Normal stars, again, in our galaxy, some of them are moving towards us, some of them are moving away from us. There's no relationship with distance, right? It's weird that the universe is ordering itself in this way. The further away a galaxy is from us, the faster that galaxy is moving away from us. That is the Hubble law. And you can see it in a more modern diagram here with a fairly small scatter. So let's think about this, parameterizing this line, because we've got a straight line here, and that's useful. So let's write an equation down that describes the line of the graph on the previous page. Again, it's a straight line. We know that a straight line has the form y equals mx plus b, where m is the slope and b is the y-intercept. Okay, well, let's look at the y-intercept. What is the y-intercept for this particular relationship? Well, it happens to be 0, right? The y-intercept in this case is 0. This graph goes straight through the origin. It reaches distance 0 at velocity 0. So great, b equals 0. I can ignore that part of it. That's useful. And now all I really need to do is, what is my y variable? My y variable is velocity, and my x variable is distance. I can put those into this formula, and I get that velocity is equal to some slope times the distance. And we call this slope, we give the slope a name, we call it the Hubble constant. And we give it the symbol h sub 0, or h naught. So really, the Hubble law looks like this. V equals h naught times d. Velocity equals the Hubble constant times the distance. I'll put a little box around that one, because that is the Hubble law. This is the equation that describes the relationship between a galaxy's velocity and its distance. Okay, so that Hubble constant, that slope, is actually an important thing. And it's got weird units, right? Let's draw the diagram that we were using there again. Here is velocity and distance. And we've got a nice straight line here, which is the slope, whose slope is the Hubble constant. Well, what are the units on velocity? Well, we typically measure radial velocity in kilometers per second. Cool. What is the distance? Well, we typically measure the distance in parsecs, but by the time you get out to measuring the distances to galaxies, parsecs is kind of a small unit to be using there. And so instead of using parsecs or even kiloparsecs, we often will measure the distances to galaxies in megaparsecs. Remember, a mega is 10 to the 6. So a megaparsec is 1,000,000 parsecs. So what are the units of the Hubble constant? I'm going to say units of Hubble constant. Well, the Hubble constant itself is the slope of this line. What's the slope? It's the rise divided by the run, right? And so the slope of the slope, the units of the slope have to be the units of the rise divided by the units of the run. So this is going to be kilometers per second divided by megaparsecs, which is a really weird unit, right? It's not a unit that would even really be useful in any other context but this, because you notice you've got a distance unit on top and a distance unit on the bottom, but they aren't the same. And so really, these could cancel out, and you could get a 1 over time unit for this Hubble constant, which we'll do later on, and that's going to become important. But for now, this is a number that is going to be reasonable. If we keep it in kilometers per second per megaparsec, it's a number that's reasonable, meaning it's between 1 and 100. And that's a useful thing to have. Okay, so this is the true Hubble constant. I've already written it down, but here it is again. The Hubble law is velocity equals Hubble constant times d. V is the recessional velocity, usually measured in kilometers per second. H naught is the Hubble constant. I've written 72 here, which is about what it is, but I'll say 72 plus or minus about 4 kilometers per second. Kilometers per second per megaparsec. We don't know fully what this number is. And we're still refining and revising what that number is over time. And d, of course, is the distance to the galaxy in megaparsecs. Okay, let's try this let's try this relationship out for a spin. Because once we define this, now it becomes really easy to measure the distances to distant galaxies. All we need to do is measure the radial velocity, and we can use the Hubble law to figure out how far away they are. So a galaxy is found to have a distance of 5 times 10 to the 7 parsecs. What is the expected radial velocity of that galaxy? Let's try this out. We know that v equals h naught times d. We know that d is 5 times 10 to the 7 parsecs. This is where we have to be careful, because we know h naught is going to be measured in megaparsecs. So we're going to have to get our distance in megaparsecs if we want to do this. Now, a megaparsec is 1,000,000 parsecs, right? So I need to multiply this by 1 megaparsec divided by 10 to the 6 parsecs, and that will make my parsecs go away, and I will get this in megaparsecs instead. So 5 times 10 to the 7 divided by 10 to the 6 is 5 times 10 to the 1 megaparsecs, because again, when you're dividing two numbers, you divide the bases. 5 divided by 1 is 5, and you subtract the exponents. 7 minus 6 is 1. So this is 5 times 10 to the 1 megaparsecs, but 10 to the 1 is just 10, and 10 times 5 is 50. So this is just 50 megaparsecs. Okay, we know that the Hubble constant is about 72 kilometers per second per megaparsec. We know that the distance is 50 megaparsecs. We can multiply those two numbers together to get 3,600. And what are the units on this thing? Megaparsecs cancel out. We're left with just kilometers per second. So we can use the distance, known distance, to get what the expected radial velocity would be. But it's more useful to do this in the opposite direction, right? If a galaxy is found to have a recessional velocity of 50,000 kilometers per second, what is its expected distance? Well, we can use the Hubble law to get this as well. You can try it on your own, and then you can come back and we'll work on it together. Okay, v equals h naught times d. In this case, we know what v is, and we want to understand what d is. So let's solve for d. It's always a good idea to solve these things symbolically and then plug in your numbers. It just works a little easier. So I'm going to divide both sides by h naught. The h naughts are going to cancel over here. If I bring over d over to the other side, I get distance equals velocity divided by h naught. Okay, well, that's not too bad. I know that my velocity is 50,000 kilometers per second. And I know that h naught is about 72 kilometers per second per megaparsec. If I take 50,000 and divide it by 72, what do I get? I get about 694. And what are the units on this? Kilometers per second goes away. I've got megaparsecs in the denominator of the denominator, so it comes up to the top, and that's megaparsecs up here. 694 megaparsecs. That's a really large distance. Remember, this is 694 million parsecs. So I could write 694 times 10 to the 6 parsecs. And if you know how your scientific notation works, I can move the decimal point 2 over to the left and increase this number by 2. This is equivalent to 6.94 times 10 to the 8 parsecs. That's a lot of distance. That's a really far distance. Remember, a parsec itself is 10 to the 15 to 10 to the 16 meters. And now you're talking about hundreds of millions of those stacked on top of each other. It's an enormous distance to these distant galaxies. Okay, so that previous galaxy is 6.94 times 10 to the 8 parsecs away. How long has it taken light to reach us from that galaxy? Well, that's pretty simple to calculate. If you have the distance, all you need to do is convert that distance into light years. And the distance in light years is how many years the light will have taken to get to us from that galaxy. So we know that d is 6.94 times 10 to the 8 parsecs. We know, or you can look up, that 1 parsec is 3.262 light years. And so all I need to do is multiply this by 3.262 light years per parsec. The parsecs cancel out. If I multiply those two numbers together, I get 2.26 times 10 to the 9 light years, or 2.26 billion light years. 10 to the 9 is a billion. And so, since this galaxy is 2.26 billion light years away, it has taken light that long, 2.26 billion years, for the light to reach us from that galaxy. And that's a significant fraction of the age of the universe. We'll calculate the age of the universe coming up, because that's going to be an important consequence of Hubble's law. But we're looking way back in time, and also back towards even the beginning of the universe when we look at galaxies that are this far away. Okay, I'll stop there. And in the next class, we will talk about how we can relate all of this Hubble law stuff to the structure and age of the universe itself. Okay, see you then.